Okay, this is going to be our fourth and final video in our linear momentum series. And so in this video, I don't really have any new theory to introduce. We are just going to be putting together the stuff that we've talked about in our first three linear momentum videos. So basically mostly collisions. So we're going to be talking about a collision here, except we're going to be doing this collision in 2D. So we're going to be taking some of the ideas that we've used before in handling vectors and applying it to this 2D system, breaking things up, and then solving in each direction separately and recombining it later to solve the problem. Okay, and so we can get right into the problem. It's a bit of a longer problem, so we'll take a look at just this one problem, and that'll be the end of this module here. Okay, so what do we have here? We have a rotationless collision in 2D, and so we have an object that has a mass of 1 kilogram. So object 1 here has mass 1 kilogram. It slides frictionlessly with an initial velocity of v1 equals 2 meters per second. Then it collides with an object 2 that has mass 2 kilograms, which is initially at rest. Okay. Then, after the collision, object 1 emerges from the collision with a velocity v1 prime equal to 1 meter per second at an angle of 45 degrees from its incoming trajectory. Okay, and we want to find what v2 prime and the angle theta 2 are for object 2. Okay, so maybe the first thing to do here is just to draw the problem out. So what I'm going to do is we obviously have a choice on how we want to orient our coordinates, right? So let me start by just drawing the masses. So we had m1 here. It had some initial velocity v1, right? This would be a vector, and so it then slams into this object m2. That's too small. Okay, m2 is here. This m1 smashes into it, and then what do we have after the collision? Well, we have m1 speeding off in this direction with v1 prime at some angle theta from its original trajectory, right? So this is going to be our angle theta 1. And our mass m2, we're not sure exactly where that's going to be headed, but we're going to need to find what the magnitude of this velocity v2 prime and what this angle, which I'm going to draw. So we want to kind of think of this angle as a positive angle rotating counterclockwise from the original direction that m1 was moving. So theta 2 is really going to be an angle like this, right? That would be our theta 2. Or it could be a negative angle in here going this way, right? But if we think of it as a positive angle, it's this larger theta 2 here. And so we clearly have the choice. We can apply any sort of coordinate system we want here, but the easiest coordinate system to work with would be if we put our x-axis right down the original trajectory. So that's our x-axis. And if we put our y-axis right at the site of the collision, so that'll be our y-axis, okay? And so maybe let me just take a second here to draw in some more detail. This setup here, this is what's happening before, so initially, and then our final state is this stuff here, the two masses speeding off this way here. Okay, so this is after. Okay, so that's the setup. I'm going to take a second to just write down all the quantities involved in this calculation and which ones we know and which ones we don't know, right? So we know we have m1. We know that's 1 kilogram. We have m2. We know that's 2 kilograms. We have v1. We know that's 2 meters per second. We have v2. We know that's 0 meters per second, or just 0. We're told what v1 prime is, the magnitude of v1 prime. That's 1 meter per second. And we're told that v1 prime points at theta 1, which is 45 degrees. What we don't know is v2 prime. We want to find that, and we want to find theta 2. Okay, we don't know that either. So let's keep this in mind. This is what we know and what we want to find. And let's get into the solving of the problem here. I'm just going to pause the video for one quick second, and I will be right back. Okay, sorry about that. Okay, so we want to start solving this problem. We have the setup here. We know what we know, and we know what we don't know. So we want to find the two things that we don't know: v2 prime and theta 2. Okay. So we know that this collision is definitely not perfectly inelastic, right? These two things speed off in separate directions, so it's definitely not a perfectly inelastic collision. So I'll maybe make a note of that. Perfectly inelastic collision, it is not, right? We don't know if it's elastic or inelastic. We don't know if kinetic energy is conserved, so we can't really make use of conservation of energy. We're just not sure, but we can maybe double check that later. But we still can use, of course, conservation of momentum, all right? And like all 2D problems, we're going to break this up. So we're going to use conservation of momentum, but we're going to use conservation of momentum separately in the x direction and in the y direction. So we're going to want to break this up. We're going to break everything up into its x and y components, apply conservation of momentum, and see if we can't solve the problem that way. Okay, so let's start off applying conservation of momentum in the x direction. Okay, so in the x direction, what does conservation of momentum tell us? Well, it tells us that the momentum of object 1 in the x direction plus the momentum of object 2 in the x direction initially is equal to the final momentum of object 1 in the x direction plus the final momentum of object 2 in the x direction. Okay, and again, since we know that P equals mv, this will allow us to rewrite this as follows. Okay, but we know that v2x, the original, well, we know that v2x and y are both going to be 0 because our mass 2 originally is not moving at all, right? So we can cancel that term. We can cancel that term right away. We also know that our v1x, well, all of our velocity for v1 is in the x direction, right? Mass 1 is only moving in the x direction originally, so this v1x is really just v1. Okay, we can, or maybe I'll rewrite just making those simplifications first, and then we'll go from there. So we have m1 v1 is now equal to m1 v1x prime plus m2 v2x prime, right? Except that we know that we can break up our after states, these two vectors that point, well, here, v1 prime and v2 prime, which point in the not x and y directions. We can break them up into their x and y components, right? Remember, we can just break these up into a v1 x prime and a v1 y prime. And the same idea would be true for v2 prime, right? So if we do that, we're going to find that v1x prime is actually v1 prime cos theta 1, and v2x prime is equal to v2 prime cos theta 2. Okay, and we can come back and look at the y components when we're dealing with the y direction. But these are the two that we need for now. So we can substitute that in here, and come up with the equation that we're going to see here. We're going to end up with an m1 v1 equals m1, oops, m1 v1 prime cos theta 1 plus m2 v2 prime cos theta 2. Okay, let's box this equation off. We're going to need it a little bit later. We'll call that equation A. Excuse me. Okay, let's now take a look at what's happening with conservation of momentum in the y direction. So conservation of momentum, y direction. And again, so we just start over from the beginning. Same idea as in the x direction, but we break things up in the y direction here. So p1y originally plus p2y originally is equal to p1y final plus p2y final, right? And again, because we know we can rewrite momentum in terms of masses and velocities, we can write m1 v1y plus m2 v2y equals m1 v1y prime plus m2 v2y prime. Except that we can cancel both of these terms off. Why? Because, well, we know that mass 2 is not moving at all, and there's no y component to its initial momentum. But m1 also has no y component to its initial momentum. We kind of set up the problem so that its initial trajectory is directly along the x-axis. So by design, there is no y portion to its velocity or its momentum, right? So both of these terms are 0. And maybe, well, okay, so I'll write it over here. So again, just as we did above, we know we can break up the v1 prime and v2 prime into its x and y components using these following expressions here. So v1y prime is going to be equal to v1 prime sine theta 1, and v2y prime is going to be equal to v2 prime sine theta 2, right? And if we substitute those values in and realize that our left-hand side here is 0, we're going to end up with 0 equals m1 v1 prime sine theta 1 plus m2 v2 prime sine theta 2, right? And so let's box this equation off. We'll call this equation B. And we're going to make use of these two equations to solve our problem here. Okay, another page. All right, so I have some numbers here that I'll pull out afterward. But let's start off. So we're going to let's take equation B. We could really manipulate this however we want, right? We have two equations and two unknowns at this point. The only two unknowns are theta 2 and v2 prime. And we have two equations that involve those two unknowns. So we can solve this however we want, but the way I chose to do this is I took equation B and just manipulated it so that I had v2 prime isolated, right? So I'm going to move the term with v1 prime over to the left, and then simply divide through by m2 and sine theta 2, right? So if I do that, my equation B is going to end up giving me v2 prime is equal to minus m1 over m2 v1 prime sine theta 1 over sine theta 2. And I skipped maybe one step in there, but it's probably fairly obvious. So I'm just going to call this equation C. And now what we want to do is we're going to substitute equation C back into equation A and solve for whatever value we want here. So I'm going to start off by solving for theta 2 here, since we're eliminating v2 prime, right? So let's start with that. We have A here. I'll rewrite it. m1 v1 equals m1 v1 prime cos theta 1 plus m2 v2 prime cos theta 2. And now the goal is to sum in for this v2 prime our equation C here, so let's do that. This means that we have m1 v1 equals m1 v1 prime cos theta 1 plus m2, and now this whole mess that we have up above minus m1 over m2 v1 prime sine theta 1 over sine theta 2, and we have a leftover cos theta 2 here, right? So we can clean this up a little bit. Let's divide through by, well, let's first off, we could get rid of this m2, right? Let's divide through by an m1. So we'll have an m1 gone here, here, and here. And we can clean this up a little bit, so let's do that. We have v1. I'm going to move this this term over to the left-hand side here just to clean things up a little bit. So we'll have v1 minus v1 prime cos theta 1. It's going to be equal to minus v1 prime, and I'm going to rearrange. I'm going to put both of my terms that have theta 2 as their argument together. So I'm going to have sine theta 1, and it's going to be cos theta 2 over sine theta 2. Okay? And because we know that sine over cos is tan, this is just going to give us 1 over tan theta 2, right? And maybe this is worth one more rewrite here. So let's do that. I will rewrite it. Yeah, I guess I can multiply through by a minus 1 too to clean stuff up a little bit. So we'll rewrite that again with our multiplication by minus 1. We'll have a v1 prime cos theta 1 minus v1 equals v1 prime sine theta 1 over tan theta 2. Okay? And now we're getting close. We just really want to isolate this this tan theta 2 and then isolate the theta 2. So if we do that, we're going to end up with, so I'm going to multiply both sides by tan theta 2 and then divide out whatever's left over. So we're going to end up with this expression here, v1 prime sine theta 1 over v1 prime cos theta 1 minus v1, right? And now simply isolating the theta 2, we can write it like this. So it'll be tan, well, inverse tan of v1 prime sine theta 1 over v1 prime cos theta 1 minus v1. And at this point, we're ready to substitute in numbers. We know what these all are, so let's do that. Theta 2 is going to be equal to the inverse tan of 1 times sine of 45 degrees over 1 times cos 45 degrees minus 2. Okay, and if you run that number through your calculator, you're going to find that theta 2 is equal to minus 28.68 degrees, and this would also correspond to a positive angle of 331.32 degrees, right? So if we look back at our drawing, we can see that the large positive angle corresponds to us going all the way around the circle here, and the negative angle just corresponds to us going in a negative direction, a small amount. Either one would be fine for an answer, right? So we'll take this as our theta 2, and now we want to find out what v2 is. Well, very easily we can go back to our equation C, and now we know what we always knew, what m1, m2, v1 prime and theta 1 were. Now we know what theta 2 is, so we can just substitute all that in there, and we're going to find that that we get the following v2 prime. Okay, so v2 prime, maybe I'll copy the equation from up here, minus m1 over m2 v1 prime times, what was it, sine theta 1, sine theta 2, okay. Okay, and if we substitute in numbers for that now, we're going to end up with minus 1 over 2 times 1 times sine of 45 degrees over sine of whichever one of these theta 2's you want to use, either the negative angle or the large positive angle. If you make those substitutions and plug it into a calculator, you'll find that your v2 prime is actually 0.74 meters per second. Okay, so let's take a look at this and see if this makes sense. We have both of our objects initially. One is at rest, so M2 is at rest. M1 smashes into it. They go off in two separate directions. The angles make sense, right? The initial, the final angle, our theta 1 for M1 had it going off at 45 degrees over here, and we found that this thing would be going off at a slightly sharper angle. I think it was minus 28 degrees or something. Yeah, minus 28 or 29 degrees. So this thing is heading out a little bit more similar to the original trajectory. We find that, well, we're told that v1 prime is 1 meter per second, and v2 prime we find is 0.74 meters per second. So the whole thing seems to make sense. These things are moving in ways that we would intuitively expect, right? So now we weren't asked, but we can take a look at the kinetic energy in this situation here. So we're not told if this is a collision which is going to preserve kinetic energy or which is not going to preserve kinetic energy, right? So either a totally elastic collision or not, right? So let's take a look at what happens with kinetic energy and just see whether or not this is an elastic collision, or if not, how much of our kinetic energy we lose in this collision, right? So basically, we're going to look at the change in kinetic energy just for fun. We know the change in kinetic energy can be written as kinetic energy final minus kinetic energy initial. And well, let's take a look at what kinetic energy initial is. Kinetic energy initial, well, the kinetic energy initial is only going to be the kinetic energy of that first mass, right? Because the second mass starts off stationary, so it has no kinetic energy. So we know this is just going to be kinetic energy of our first object, which is equal to 1/2 m1 v1 squared. That was 1/2, m1 was 1, v1 was 2, so 2 squared, so this is going to be 2 joules, okay? And kinetic energy final is going to be, well, the kinetic energy of object 1 final plus the kinetic energy of object 2 final, right? And this is just going to be 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. Okay, and we can just put numbers to that right away. I'll factor out the factor of 1/2. m1 was 1. v1 prime was also 1, so we'll square that. And m2 was 2. We just found that m2 prime is 0.74, so we'll square that. And if we were to calculate all that, we would find that this was 1.04 joules, right? And then just going back to our original equation here, we can substitute in for kinetic energy final and kinetic energy initial. So we have kinetic energy final is 1.04 minus our initial kinetic energy of 2 joules. This ends up giving us 0.96, or I should say negative 0.96 joules. So kinetic energy is not conserved in this collision. We can see from our calculation here, we actually lose almost half the kinetic energy that we had. We lose 0.96 joules of our kinetic energy. And so we could say something about that if we wanted to. If the question was worded differently, we could answer things about lost kinetic energy. Maybe the last note is that if we weren't given some of these variables up here, let's say we weren't given, I don't know, v1 prime or something, right? We could have solved for these three unknowns if we were then told that the equation or that the collision was elastic, right? So then we would have access to a third equation. We could use conservation of energy to give us a third equation, and we would end up with three equations in three unknowns, and we could solve that by using that combination of three equations. Okay. But we'll probably see more of those. Well, questions like this will definitely come up in the assignment and midterms or finals. So make sure you know how to do these, and I will see you guys in the next module.